Hey everyone, my name is Johannes, and this is my second video about how to interact with your compiler. And today we're going to look at a flag that you probably always want to include when you do anything that is performance critical in your C++ compilation process. So what we're going to look at is the same code we had last time, which is just a benchmark that I made up. It really doesn't compute anything meaningful. The whole purpose of this is to show that a computation can be sped up depending on the flags that you pass. Last time we've seen that, the different optimization levels like O1, O2, or 3 have an impact on the performance and the number of instructions that have to be executed. Today we're actually going to look at performance measured by time, and we're going to look at a specific flag and how that impacts the time and why it does. So first, we're actually going to compile this piece of code, same way we did last time. We just say O3, give it the file. We ask the compiler to tell us remarks about loop vectorization. So this basically says, hey compiler, whenever the loop vectorizer pass does something, please give us a remark about it. We're interested. And then we store this into optimization levels client-plane.out. Let's do it. And what we're going to see here is a remark that in the source file in line 13 at column 5, which is basically the position of this loop here. The loop was vectorized by the vectorizer, and it shows a vectorization width of 2, which basically means 2 iterations are executed at the same time in lockstep in a vector fashion, and it interleaved 2 iterations of the loop. So it basically executes, the first instruction, and then of the first 2 iterations that are executed in a vector fashion, and then executes the first instruction of the next 2 iterations. That is what the interleaving comes in, and then moves on to the second instruction and so on. Okay, so that is our base case. So if you just say O3, which is what a lot of benchmarks out there do, but that is really not what you should do, because when you just say O3, the compiler doesn't know what kind of CPU architecture you really target. This is compiled for a very modest, very default, very standard x86 64 CPU. So what you want is to tell the compiler what architecture you're targeting actually. And you can do that with this command line flag, and what oftentimes is sufficient, just say native, which will tell the compiler to just look up what the CPU is you're running on. So given that I don't cross compile, this is what I want to do. So I'm going to do native. And what we see here is that it is vectorized again, but this time the vectorization width and the interleave count have changed. They're both 4 now, so they're doubled. Why is that so? Because this processor actually supports wider vectors than the default processor that was targeted earlier. And because the compiler knows that this processor supports wider vectors, it shows a larger vector width. Let's take a look how that plays out when it comes to time. We're going to use perf to do the timing here again. We're asking it to give us statistics, and we're going to ask it to give us kind of all the default statistics this time. And we're going to tell it to run the program 11 times and give us, average values and errors. So we'll see the printf that is in the program 11 times. And then afterwards, it tells us about all the events that it captured by default. Perf can capture all sorts of events. So this is just, the default set. Let's for a second just look at the time, which is the very last line here, which basically says it took on average 0.179, so almost 0.18 seconds on average to execute this program. Okay, That's our baseline. That happens if you don't target a specific processor, but just the default. What happens if we execute the specialized version 11 times? So we can see a printf. And now what we see here is it only takes 0.1592, so kind of close to 0.16 seconds, which is, let's just do the math real quick. Is like a 12% difference. So we're looking at a 12, almost 13% difference here in this, micro benchmark that I obviously made up. But we're looking at this difference because we told the compiler what architecture we're really targeting we're going to run on. And you should always do that. And if benchmark results don't tell the compiler what architecture they run on, those benchmark results are really not very meaningful. Okay, that's it for today. Thank you very much. See you next time.